So we're looking at chapter 6, and we're doing part A, and we're going to start with number 5. So we're going to do A5. So again, we're going to write our given, and we're going to write our find. And when we read our given, we're going to chunk. We're not going to read everything at once because we might get confused. So it says a car weighing 15680 newtons, so that's the weight. F of little g is equal to 15680 newtons, and is moving at 20 meters per second, so that's my initial velocity, is acted upon by a 6.4 times 10 to the 2 Newton force. So again, I'm going to chunk. I'm going to read. I'm going to write. So this way I'm not going back and hunting for stuff in my problem until it's brought to a halt. So even though they're not telling us a number, that means something. So the final velocity is 0 because that's what coming to a halt means. A, what is the car's mass? B, what is its initial momentum, which is pi? C, what is the change in momentum, delta p, because delta means change in, and D, how long does it take the braking force act on the car to bring it to a halt? So there's many parts to this problem. So now I wrote down all my givens. So part A, I want to find the mass. So the first thing I'm going to do is I'm going to write my basic equation. We know weight is mass times gravity. Instead of just plugging in and doing algebra in my head, I'm going to rearrange the equation to solve for the unknown in terms of the known. So mass is equal to the weight divided by gravity. Now, I know the force of weight acts down, and I know gravity acts down. So if I'm using my sign convention, I would make them both negative. If you don't, and you just remember that, because the negatives would cancel. But I don't have to get hung up on my sign convention right now, because I just want to find the mass. And mass is scalar. It doesn't have a direction. All right, now before I put my numerical answers, remember in physics, you have a foolproof way to check your work every time. So if you carry your units and cancel, it checks your work. So a Newton is actually a kilogram meter per second squared. So what I can see is that this meter per second squared cancels this meter per second squared, and I end up with kilograms, which is the correct unit for mass. So when I do this on my calculator, it says 1,600 kilograms, and then in my correct significant figures, I would have the mass as 1.6 times 10 to the 3 kilograms. So that's part A. Now let's look at part B. Part B says, let's find the change in momentum. Well, it says find the initial momentum. So the initial momentum is pi, which is going to be mvi. So that's going to be 1.6 times 10 to the 3 kilograms times my initial velocity, which is 20 meters per second. So when I multiply that out, I get 32,000 kilogram meter per second, and then in correct significant figures, I'm going to have pi is 3.2 times 10 to the 4 kilogram meter per second. So remember, whatever I do to my number, I do to my unit. So my unit is kilogram times a meter per second, which is the correct unit for momentum. Part C says find the change in momentum. So change is delta. So delta P is going to be m delta V. So what I'm going to do is I'm going to stretch this out. So it's going to be m VF minus VI. So delta P is going to be m 1.6 times 10 to the 3 kilograms times VF, which is 0, minus 20 meters per second. Now, if I use my negative, then I would get negative 3.2 times 10 to the 4 kilogram meters per second. And that's just the change. And then the last part, part D, says how long does it take the braking force, how long does the braking force act on the car to bring it to a halt? So I want to find the time. This is where I'm going to use the impulse momentum theorem. So the impulse momentum theorem is Ft is equal to m delta v. Now there's a delta in here, but usually they give us a time interval like this, or that's what we want to find. They don't give us an initial and final time. So now I'm not going to plug in numbers. I'm going to rearrange the equation to solve for the unknown in terms of the known. So T is equal to m delta v over f. Now so I already found delta p is m delta v. So I already found this here. So this is going to be 3.2 times 10 to the 4 kilogram meter per second. Now this is negative, okay? And then the force is going in the opposite direction to stop it. So the force is actually a negative force. And when I put my negative sign in here, the negatives cancel out and I get a positive value for time, because time, we can't go backwards in time. Now before I multiply everything out, again I want to look at my units. So a Newton is a kilogram meter per second squared. So this kilogram cancels with that, this cancels with that, this cancels with one of those. So for my unit, I end up with 1 over a second. So 1 divided by 1 over a second is the same as 1 times a second over 1. So it comes out to be a second, which is the correct unit for time. So T comes out to be 50 seconds. So again, if I carry my units through and cancel them, I have a foolproof way to check my work in physics. And that's what makes physics so easy. You always have ways to check your work.